Okay, morning. So, we will begin today's lecture. Yesterday, I was talking to you about Reed's method of defining any function, be it one dimensional, two or three dimensional, knowing the values of some the so called function at discrete points. First of all, we do not know the function, we know only some discrete point values. So, knowing that, the Reed's method came out to be very handy, that any general function, now whether it is one dimension, any function phi it can be one dimension, it can be written as ni x. So, if you have, this is not equal to sign, as I told you yesterday, this is approximately, because I will be only finite. So, I will be going from 1 to n. Of course, if n tends to infinity, then it will be exact, then exact, then equal to sign exact. We cannot have that condition, therefore, it is always. So, number of data points are known. So, this is a very general description of Reed's approach, and this was not known to finite element people in the beginning. See, when finite element started in 1956, and then even in 1960 when the first presentation was given by Ray Clough, this was not in the picture. What they used to say is, yes, any general function. Now, I am giving you example of one dimension, it can be also a three dimensional function, x, y, z can be written as ni, and yesterday I gave you some example of why this relation is holds good, because if the property of ni is such that property of ni is such that nij, now we will have to introduce, is equal to 1 when I equal to j, equal to 0 when I is not equal to j. This, of course, I and j has to be suitably introduced. So, that, but here we are using only one subscript. So, if this is the property, then we found, yes, and these functions are easily constructed, because they represent some kind of shape, and so this is to the credit of Reed's. But when finite element is started, this was not used. That time any function was said okay, because basically you have to approximate a function. We wanted, what was our main aim? We have a domain or a subdomain, an element or the total, and we would like to represent the variation of my displacement here within this domain or subdomain in terms of nodal parameters. This is the objective of this. Can I express u x in terms of nodal parameter? Yes. Now, this is a function of x, because x is varying from here to here, but these are the data points, these are the fixed nodal points. So, this was the objective. So, earlier when finite element is started, the best way one can think of how to represent a function was, yes, you can express a function f x as a0 plus a1 x plus a2 x square. Polynomial is the best way to represent to a n x n. Of course, this is infinite. Any function can be represented in this infinite series. Again, this we will not be able to take the entire infinite number of terms. So, we always truncate it. So, any function can be represented by a linear function, quadratic function, cubic function, quartic function, etc., depending upon how many terms you take in this polynomial. So, polynomial was the simplest polynomial representation, polynomial representation of a function. This was, but then here all these a 0, a 1, they have no relationship with nodal quantities. There is no relationship of this coefficients of polynomial, x 1, x 2, etc. I mean sorry, x square, x cube coefficients. There is no relationship, but they are undetermined coefficients. They are general coefficients. So, but a function was used like this in terms of what we used to call in the beginning generalized coefficient. These are generalized, generalized coefficients. So, in terms of polynomial coefficient. So, it was, but then in order to bring in a relationship between a 0, a 1, etc., to nodal, we can see, yes, that it is possible to relate the two in some way. And later on it became clear that there is no need to start assumption of a function like this. We can directly go to the Ritz approach. Ritz had already done this approach long time back. And you see, it always happens in literature. Somebody does something and it remains within the journal paper somewhere, unless somebody opens it and sees it. If Ritz had done, then some of his students might have known, then something. Now, if you do not follow it something, then it is forgotten. So, many times things are forgotten for several years and then suddenly you realize, oh, this was done by so and so. So, why can't we use Ritz approach directly? Why? What is the need of using a polynomial function? But then I will tell you, let me take this example of two noded rod element, because we are discussing actually, I am explaining everything with reference to your axial rod. So, let us take this is my element 1 and 2 u x. Sometimes I am using phi and other time phi means a general function, u means it becomes a displacement. U, the moment we say u, we are used to representing u by some displacement. So, but function is general, anything. So, u1, u2. So, if you want to, so we can start like this. I mean, yesterday we did it. I gave you also the what is the value of n1, n2, but then I can say that u x can be started. Let us assume polynomial of a 0 plus a 1 x, because I want to express this function in terms of only two nodal quantity. Between 2 points I can have only a linear straight line. For those of you who have already done other courses, you will know it, but then I think it is required for some of those of you who are attending this course for the first time to note this approach. So, between 2 points, two data points, I can only draw a straight line. So, best thing is to take an linear function, polynomial. But then I have got, so let us, so this is an assumption. Let u x be approximated at a 0 plus a 1 x. But then I also have that, yes, u at, if this coordinate is x 1 and this is at x 2, this coordinate of nodal point, u at x 1 is u 1, and therefore, u 1 is equal to a 0 plus a 1 x 1. So, one equation we got, this is boundary condition. Similarly, u at x 2 is u 2 nodal equal to a 0 plus a 1 x 2. So, I have got two equations. These are two equations and there are two unknowns, two undetermined coefficients a 0 and a 1. They can be solved, they can be. So, a 1 and a 0. So, let us try to do this. So, let me subtract the two equation, so that a 0 will get cancelled. So, I will get by subtracting 1 minus 2. what you will get? You will get a 1 into x 1 minus x 2, because this will get cancelled, equal to u 1 minus u 2, and therefore, a 1 is u 1 minus u 2 divided by x 1 minus x 2. You can also write this, many times we always write down any difference of two quantities, we always write the final value minus the initial value. And in our scheme of things, u 1 is the first, u 2 is the next point. So, you can also write this as there is no change, sign. So, 1 you got, and once you have got this, therefore, I can get other constant a 0 for example, let us say equation 1. Equation 1 a 0 is u 1 minus a 1 x 1. So, what is a 1? A 1 we have just now found out. So, it is u 1 minus a 1 is u 2 minus u 1 x 2 minus x 1 into x 1. So, you see here now I have got, that means the coefficients can be obtained in terms of nodal parameters and the coordinates, nodal coordinates. So, this one can be simplified, I believe. Can somebody simplify this? It will be u 1 x 2 minus u 1 x 1 minus u 2 x 1 plus u 1, I have just expanded x 2 minus x 1. Just see whether it is right. Have I made any mistake? No. Is there any cancel? u 1 x 1, u 1 x 1, yes, this one and this one will go. And therefore, you get here u 1 x 2 minus u 2 x 1 divided by x 2 minus x 1, x 2 minus x 1, yes. So, you see this is, so you have got now both the coefficients, both the undetermined coefficients in the polynomial. So, understand, understand the physics step by step, how a function can be represented by two parameters, then we can use this. Of course, this is the simplest, you cannot have anything simpler than a linear function, 2 points. You are expressing a function between 2 points, that is all in terms of those 2 nodal points. So, what you just join them by a straight line. So, but we have to do so much of. Now, therefore, u x, and therefore, we have got already, therefore, u x is a 0 is u 1 x 2 minus u 2 x 1 divided by x 2 minus x 1 plus a 1 x. A 1 is how much? A 1 is u 2 minus u 1 divided by x 2 minus x 1, and it is x. So, this is your now see, now you see there is no here, this is divide of a 0 and a 1. A 0 and a 1 have been replaced by what? X 1, x 2, u 1, u 2. These are all nodal parameters. So, our aim has been to express the function, general function, variation of displacement within the element in terms of nodal parameters. Nodal parameters can be anything, it can be displacement, it can be temperature, it can be pressure. So, anything that comes, it we can always express. Now, it is okay, u 1 x 2 everything, but I think we can still do something to bring it in a proper form. So, what I will do, we will take coefficient of u 1 at one place, what are the coefficients of u 1? So, u 1 at one place and u 2 at another place. So, coefficient of u 1 here is x 2 by this and here minus this. So, yes. So, it will be coefficient of u 1 is x 2 here divided by this and minus u 1 x divided by this. So, minus u 1. So, minus x 2 minus x 1 into u 1. So, coefficient of u 1 is it is okay. What about coefficient of u 2? U 2 is here, u 2 is this coefficient 1 and then minus is here. So, I will have a positive only in the beginning. So, positive means what I will do, I will have x, this one x divided by x 2 minus x 1, this term is coming and here it is x 2 minus x 1 u 2 minus x 1 into u 2 into u 2. Yes, this is how it is coming. So, there are two coefficients that have come, these multipliers. So, they should be, knowing Reed's method now, they should represent the multipliers of Reed's coefficient. These are nothing but, they should be nothing but n 1, n 2, n I phi I, n I u I. So, this must represent n 1, this must represent, that means we have to check whether this property is same as that of n 1 and n 2. And I think we can see this, it should be same. What is the value at x equal to, for example, this coefficient? What is the value of this variation of this first bracket between the two node? When x equal to x 1, what is the value? Unity. So, it is unity here at x equal to x 1. When x equal to x 2, what is the value? X 2 minus x 2, 0. So, 0. Between 2, you will always have a linear. So, this is a linear function. So, this is your this is, and obviously, this is nothing but same as whatever we had just learnt n 1 x. So, Reed's was more forward, than he had given directly that relationship. Any function can be represented like that. So, now here same thing, now you come to the second one, second bracket. This, when x equal to x 1, what is the value? X equal to x 1, it is x 1 minus x 1, 0. When x equal to x 2, it is equal to unity. So, again here it is, this is unity and this one is your, and this is nothing but n 2 x, shape function for node number 2. So, this is shape function. In short, we write shape function for node 1, shape function for node 2. So, therefore, I think I can also get the yesterday's relation. If x 1 is 0, if x 1 you take 0 and x 2 minus x 1 is L, x 2 minus x 1 is the length of the element L, then what will be this? I think yesterday, because yesterday I have given it for that, na? So, that should also come. So, same expression, when x 1 equal to 0, x 1 means origin comes to this point itself in the beginning of the element. If the origin coincides with x 1, then, and the difference, this one is L, then I want to express. So, here it is x2 means what will be x2? Then x2 also will be equal to L, because anyway x1 is 0, x2 minus x1 is L. So, x1 is 0, so x2 is L. So, it will be first one. So, therefore, this n1 will be x2 is L minus x divided by x2 minus x1, that is L. So, that is 1 minus x by L. I think yesterday I gave you this. So, it coming. Similarly, here N2 is this x minus x1 is 0. So, it is 0 x divided by x2 minus x1 is 0. So, x2 is how much? L. So, yesterday also I gave you this. So, they are exactly the same. So, this is so shape function can be assumed either as starting with polynomial, but then you can always bring it in this form by putting the boundary condition, or directly you can start from the Ritz method, which is a general method for if you know the nodal parameters, you can always express, you can always pass a curve, a surface, etc. through those points by ni phi I. So, this was a great realization after several years, after 19, I do not know exactly, but this is not in 60, by I think 1965, 66 people started using in the form of n. Earlier all the derivations were in terms of A0, A1, A2, etc. and they have no physical meaning, while nodal parameter has a physical meaning, displacement of node 1, temperature of node 1, A0, A1 have no physical meaning. So, there was some. So, this is more appealing, this using in the form of Ritz. Okay, so, first is the infinite element method is always establishment of displacement field within the domain. Now, domain is always very big. Why finite element? Because I am expressing now, I think I have given you already the concept. Domain can be very complex, but then subdomain, that element can be a simple one. That is the basic idea. And if it is a simple one, you can understand it better. You can write down the equations, governing equations, you can understand it, solve it, find out the relationships, and then combine them all together. So, first step in FEM is establish the displacement field within the element. So, here for example, so first step is 1 displacement So, that means within the element, now my element is a very simple linear element x. So, this is, and I will now introduce something, some notations to give you some generalization of FEM. So, u is the displacement within the element running from node 1 to node 2 having length L. So, I am approximating that. So, let us say that I want to get an approximation of this u and call that approximation as u hat. So, I will always use a quantity with hat quantity as approximate. So, actually in any numerical method including finite element method, you are dealing only with approximate quantities. There is nothing exact. Exactness, you should forget about exact. It is approximate and it is depends upon your ingenuity, how good, how close to the true value you can come to. So, we are approximating u to u hat, and u hat now I can write u hat x can be written as for my two noded rod element, axial rod element, two noded axial rod element, I can write this as n1 x into u1 plus n2 x into u2. Is it clear? Here I can use a equal to sign, because I am writing approximate. But if you are writing here left hand side u, this has to be, is it okay? So, first you establish this, and then we have got this, yes, that yes, n1 n2 consists, how do they look? So, first stage in finite element, we write this in matrix form. I think yesterday I gave you that yes, this can also be written as a n times d, where n is a matrix n1. Even if I write, even if I do not write function of x, means all the shape functions are functions of x space, and d is u1 u2 transpose. I can write it like this. Either I can give transpose here and then like this, because D is defined as a column. DI we always define as a column, not as a row. These things are important. It is not that anything you define as a row and column. No, you have to be careful. What is column? What is row? So, this is ND. So, this is established. So, first you please find out, establish this N. First step is established. Once you have established, then second stage in FEM, second 2, we are talking of displacement based finite element 2. After you know the displacements approximately within the element, what you can find out in any elastic, because we are dealing here with elastic continua, elastic body. Rod is a elastic body, simple one dimensional elastic body. So, next one what you would like to, from displacement we would like to find out is strains, that can be. So, next stage is please compute strains and in the body. I think you have a background of theory of elasticity, and you should have, those of you who do not have background, you must read theory of elasticity first 3-4 chapters, and you should know all the basic equations of elasticity. So, next is strains. So, in a rod, in an axial rod, out of 6 strains, generally we are not talking of 3-dimensional body, I am taking a simple body. So, in an axial rod, the only strain component that is present is epsilon x along the length of the, because this is x direction, this is 2. So, it is only epsilon x, there is no arrow here, but I just because strain is not a vector. So, it is only epsilon x. So, epsilon x is, how will you find out epsilon x? Epsilon x is derivative of displacement. So, it is du of dx. Why I have used here total derivative, not partial derivative? It is only one dimensional, otherwise it is a partial. It is one dimension, there is no other variation, everything is only, all quantities vary only in, are varying with respect to x only. So, du by dx. So, du by dx, so you have already got. So, can I write this du by dx like this? You already have n here, n matrix and u and d matrix here. Horizontal was n and d. Of course, d, there is no question of derivative of d. Derivative d means u1 u2. Those are nodal displacement. You cannot take derivative, that will be 0, fixed quantities. But n are functions of x. So, I can write down here directly, because d of this one. So, I can write down this dn1 by dx, dn2 by dx times u1 u2. So, this can be written, I could have written also before this d upon dx separate u here. Of course, there is only one quantity, so it does not. So, there is a derivative which is coming here. Yes, okay. Anyway, this is all right. So, this is n 1 n 2 d n 1 and so this matrix derivative of the shape function matrix in finite element terminology, I mean in jargon, it is called a B matrix, B strain matrix, because this is the matrix when multiplied with nodal parameters gives you a strain. So, this we will call a strain matrix. So, I will call this one is a B matrix, B. If you read any book of finite element, so that is B times D, where B is dn1 dx So, it is a derivative matrix, it is called also a strain matrix. So, you also have to establish B. So, this is next stage in finite, because D anyway is the basic, everything we want, our aim is to express everything in terms of nodal quantities, all. The whole formulation should be in terms of only my basic parameters, quantities in the whole formulation. I know only my points where I have measured I have taken the data. So, I know only nodal points. So, let us express everything in terms of D only. So, this is also to be established. So, next stage in finite element is establish this B matrix. This is important thing. In any problem, you please establish this B matrix. So, first is n matrix, because unless you establish n, you cannot proceed further. So, then B. Now, B we have just now said, for example, here B is 1 let us take that your n 1 n 2 for the linear, because it is, let us take 1 minus x by L and x by L. Okay. So, derivative of 1 minus x by L is how much? So, minus 1 by L, and derivative of x by L is how much? So, this matrix is this. B matrix for my linear rod element is minus 1 by L and 1 by L in terms of geometry. It so happens that it is constant here, it need not be constant. We see, just because we are having a linear function, that is why it is constant derivative. If had it been a quadratic function, d upon dx would not have been constant. So, this B matrix in general will be a function of x, it will be a function of space. Here it is, because of our linear assumption, it is constant. Okay. Next step in finite element, that is step number 3. So, any problem, no matter what problem in elasticity you are tackling, these are the same, steps are the same. So, next what should we do? Yes, next. Okay. strain we have done constitutive, stress strain law. What is the relationship between stress to strain at any point within the element? Strain now we have got, now how it is related to stress at that point, any point within stress strain relation of point base. So, we call it constitutive relate stress to strain. Of course, I do not want to go into the details of derivation of stress to strain. Please read it. I have already given it in the other course also. So, in general, you can at any point you have 6 components of stress and 6 components of strain. So, you have a E matrix. So, normally strain, if you have a strain in general, if you have strain which is in general is epsilon x, epsilon y, epsilon z, gamma x y, gamma x z and gamma y z. These are the components of strain. So, we express them as a strain vector. Similarly, stress vector we represent the corresponding stresses at any point will be sigma x, sigma y, sigma z, tau x y, tau x z and tau y z. So, this is coming on the screen, no? Okay. So, then this one we relate strain to stress, and then we can always establish a matrix 6 by 6 S matrix, and then here we can have what is S matrix called? S matrix? Compliance. It is similar to flexibility matrix. Compliance. How compliant is the material? How flexible is the material? Compliant. Material is compliant. Compliant matrix or flexibility matrix of the material. This matrix is easy to derive. I hope each one of you should be able to derive S matrix from first principle for a general state of stress and strain like this, each one. And inverse of this we denote it by this, we denote it by this, or sometimes another letter, this C. C is called what? Inverse of S. C is inverse of S. That will be similar to stiffness of the material. So, this is called stiffness matrix. This is not easy to derive directly. We always write down this and then invert, then C matrix. But this matrix, this relationship is easier to, it is normally used in all the formulations. This form is more convenient for derivations, etc., while this one is for deriving. So, we will use. So, for our rod, 2 nodes, point P at x, you are having a displacement u, and you are having a strain here and a stress here, only one component, not all the 6 components. So, stress and strain will be related by a simple Hooke's law, not generalized Hooke's law, simple Hooke's law of only one. So, it will be given by this sigma x will be material Hooke's, Young's modulus of material multiplied by, there is no question of, so this E times epsilon x, and so sigma x is this E times epsilon x, and we have just already found out that epsilon x is B times D. So, we can also write this is equal to B times E B. So, E B into D. So, if I want to write down in matrix notation, so it will be like this. It so happens it is only 1 by 1 and this is what? No, B is not 1 by 1. This is 1 by 1, this is 1 by 2, this is 2 by 1, then only they can be multiplied. See, this is a scalar here. So, this is 1 by 1, this is 1 by 2 and this is 2 by 1. So, final quantity is only 1. This is single scalar 1, but you can write a general formula that yes, sigma equal to E B D. So, now here stress also I have expressed in terms of displacement, nodal displacement. Okay. What is the third most important? So, this is 3, this was strain, displacement, yes, this was 3. What is the fourth one? Fourth relation in elasticity that need to be satisfied? Equilibrium. Equilibrium, element must remain in state of equilibrium. How to ensure that? One is writing down the equilibrium directly. In the other course, we have done the equilibrium of plate element directly by showing all the forces on the element which are keeping the plate element in equilibrium, and then writing down the 6 equilibrium equations. We found that only 3 were non-zero. So, we have got the 3 equations of equilibrium. One is direct, but this direct approach is all right, but it works only for simple problems which you can visualize. The moment there is some complication, this direct approach fails. We will not be able to visualize, what is the kind of force that will come there, and then. So, there is an alternative way of satisfying, alternative way of equilibrium. So, equilibrium condition, that is 4. So, one is direct approach, which we all know, show all the forces on the body and then take equilibrium. Sum of all forces equal to 0 moment, and other we will use indirect. So, I think indirect method is more useful because it will work for all kinds of problem, simple and complex. So, indirect. How do you satisfy equilibrium? If a body is in a state of equilibrium, I think this figure is should be known to most of you. This is a very important figure. It is not that it is only you study in physics and then matter ends there. No. These are three stages of equilibrium of a rigid sphere, rigid disk. There we study only, I think, rigid, not deformable in physics. Rigid body mechanics we do. So, rigid body. So, if you have a body and then this body is kept on 3 types of surfaces. One is a bowl like this, other one is a convex surface like this, and on the top of the hill you are kept the sphere. So, everything, all the three states are in good, body is in, appears to be in equilibrium, but actually all the three states are equilibrium states. But the most important is this, unless you are in this state, you are not, what should you say, you are fragile. If you are not in this, then that other two states are fragile. Because here if I move this over here, so this will have two component, one perpendicular to this. So, there will always be a restoring. Now, here when this moves to a new position, well, here also it is same. Here when it moves to a adjoining state, you have one component here and you have one component here. What is this component called? This component is very important, this. Similarly, this component, what you will call this? Is there any difference between this component and this component? What is that? Which force? No. Yes, one is restoring, other one is deflecting or non-restoring. I don't know what is the opposite of restoring. Non-restoring, deflecting. So this restores. See here, no matter where, whatever you do, sphere will always come and settle down here. Disturb it to any position, it will always come back to this bottom. And bottom here, potential energy Pe. Pe is, you just see. Now, while here, you see, if you deflect it, this force will take the body away from the equilibrium position. So, there is a restoring. It will never come back to this position. Okay? And potential energy, you see what is happening. In fact, this was the maximum potential energy, highest point. As it comes down, so lower and lower. So, it will come and stay somewhere when there is a lower potential, somewhere here it will come and stay when it finds that yes, it has come to a flat. So, this is the highest potential energy, this is the lowest. So, if a body have a highest very lot of potential energy, then it is in dangerous state. Yes. So this is the condition in which this is a neutral. So, this is called stable, this is neutral and this is unstable. So, there are three states of equilibrium, all these three states are equilibrium states only. So, one of the principles of equilibrium is indirect, is that a body will be in a state of equilibrium if it has its potential energy minimum, minimum potential. So, it is called principle of minimum potential energy, principle of minimum. So, please read this, minimum potential Pe, potential energy. And for a deformable body potential energy minimum, see first of all a potential energy, total potential energy of a body consists of two deformable body. One is strain energy, strain you know energy of deformation. So, if you denote it by U, U is the strain energy, and then you see, and then when whatever forces that act on the body, they do some work in deforming the body. So, that is called work done by external forces. Okay. So, that is of having a work done. Now, strain energy is something that gets stored, body gets deformed, when you release again it comes back to its original position, if it is a linear elastic material, you know. Now, but the strain energy minus the work done, if you denote the work done by W minus the work done external, this is due to external load, external work done, and this is strain energy, that we define this as potential energy of the body, and we denote it by a letter, by a symbol pi, capital pi. This we call as potential Pe. Pe is pi equal to U minus W, strain energy minus W, work done by external forces. Why should W be negative? And then we call that as potential energy. See, I will just tell you here. Supposing this body is there, it has a, you know, you have to measure the potential energy from some datum. Now, if I take the body up, the load is acting downwards. I am just giving gravity load. So, I am taking that, my datum has remained the same, datum is same, this desk, you know, I am taking from here to here. So, what is the kind of work done? Negative work done, because force is acting this way, I am moving upwards. So, W minus displacement is work done, but negative, because they are not in the same direction. This is acting downwards and I am moving upwards. So, negative work done, and I have come at this level. Now, then I will say that potential energy of my body has increased. Why? So, minus work done. Now, when you come down from this level to, let us say, this, work done will be positive, and I will say potential energy has decreased. So, there is always a negative between work done and potential energy. This concept must be kept in mind. Okay. So, that is why this negative thing comes here. So, this one you please make a note, and then we will complete this the next time. Okay. Thank you very much.